Okay, hello everyone. Today I'll be presenting my work on a study on the lifecycle of flaky tests. This work is done by me, Wing from the University of Illinois, along with my collaborators Kavanch, Hitesh, and Suresh from Microsoft. So what is a flaky test? A flaky test is a test that passes and fails when it's run in the same test scenario. On the right-hand side of the slide, we have a simple example of a flaky test from a Microsoft product. In this case, the test is flaky largely because of this line, line number 9 here. Specifically, the question here might be, how does this new random.next actually generate a random number when no seed is given? And the answer to that is that it actually uses the system timestamp as the seed. So why is this problematic? Well, because if line 9 is actually invoked very close together, in fact, less than 15 milliseconds, then it will actually give you the same ID. And this is problematic because, as you can see from line 6 is actually checking whether or not the 2 test alerts created at lines 3 and 4 actually have the same test ID or not. And it would fail the assertion if the 2 IDs are the same. So the issue with flaky tests is that developers typically are making some changes and then they're rerunning a bunch of their tests. In this case, in the presence of flaky tests, if they have flaky tests in their test suite and a test fails, they may not actually know if the test failure is because it's a flaky test failure or if it's because it's something to do with their current changes. And this then consequently makes it so that developers have to waste time debugging their current changes and or rerunning tests. So the contribution of my work here is to actually help proprietary software developers with flaky tests. Specifically, I help them by first performing a study to characterize flaky tests in these proprietary software. And then I will present an approach to help them balance the runtime and frequency of these flaky test failures caused by these asynchronous calls. For my study, we look at actually 5 main categories of flaky tests, questions related to flaky tests. Specifically, the first one is on prevalence. So how prevalent are flaky tests and to what extent do they actually impact the developer's workflow? The second one is on the detectability. So how many runs are typically needed in order to find these flaky tests? The third one is on characteristics. So does test flakiness reoccur? And whether or not the runtime of these flaky tests actually differ between passing and failing runs. The fourth one is on categories. Specifically, we look at the root cause and location of flaky test fixes. And finally, we take a look at how much time developers take to fix flaky tests. And then we also take a look at how developers are actually currently fixing async wait related issues in flaky tests. So for the purpose of the presentation, we'll largely just focus on the questions in categories and resolution, but I do encourage you to check out our paper for the other research questions. In terms of the categories of flaky test fixes, for 6 of the projects, we find that the majority of the fixes are in the test code. We find that the most common category of fixes is async wait. For those that are unfamiliar, async wait related flaky tests are essentially tests that makes an asynchronous call and they do not properly wait for the asynchronous call to return before they utilize the resource. Our findings essentially from this research question is similar to what has been found by some previous work that was done on open source software. Specifically, we find that test code is where fixes are typically made and that async wait is the most common category of fixes. In terms of how developers are fixing async wait related tests, there is a blog post by Martin Fowler that proposes 3 main ways that async wait issues should be fixed. He proposes that developers should create synchronous interfaces, implement callbacks, or implement polling. And we do see from Microsoft developers that some of these are used. Besides them, we also see 3 other ways that developers at Microsoft have been fixing async wait related flaky tests, at least what they claim to be as fixes. The first one is to increase the wait and timeout. The second one is to remove the code that is related to the asynchronous call. And then the third one is to actually mock the asynchronous call. One thing I want to draw everyone's attention to here, though, is that the most popular way that developers, at least at Microsoft, are fixing these async wait related tests is actually just to increase the wait and timeout of these tests. And with that in mind, we now see that the majority of flaky tests at Microsoft are from these async wait related categories. And the majority of the ways that developers prefer to fix them is to increase the wait and timeout. So the goal of our approach here is actually to be able to suggest some time values to wait for these asynchronous calls, while at the same time, we want to minimize the rate of flaky test failures and the test's runtime. Our approach is largely in two main steps. The first one is to obtain the flaky test failure rate for the time set by the developer. And then the second one is actually to generate different time values. And then for each of these time values, we would measure the flaky test failure rate and the runtime of the test. And we will return these values back to the developer. So in terms of the input of our approach, we essentially take a flaky test along with its dependencies and the number of runs to measure the frequency of flaky test failures and the number of time values we're going to try generating. In this example, we would actually run the test 100 times to measure the flaky test failure rate for the time value set by the developer. We would then try to generate new time values based on the previous time value and that value's flaky test failure rate. So for an example, if the developer set the time to be 300 milliseconds to wait for an asynchronous call, and we find that there are 0 flaky test failures from this value, then the next value we will try is 150 milliseconds. Essentially, we are binary searching our way for these next values. In terms of the output of our approach, for each of the time values that we tried, we would actually output that along with the runtime of the test and the flaky test failure rate. When we actually apply our approach to 5 async wait fixes and their tests, we actually see that our approach can reduce the running time of these tests by 38% on average, while keeping the flaky test failure rate to still be at 0. And we actually see that for one of the tests, we can reduce the running time by up to 78%. We also see that for 4 out of 5 of the tests, the time value, when we actually change it, even though the developers claimed that this flaky test is related to a time value, when we actually change the time value, we actually see that the flaky test failure rate is not affected. And it's important to note here also that for these tests, they were all ran on the continuous integration server where the developers are actually also running their tests. Our manual investigation into these fixes also finds that the developers really thought that increasing the time value would reduce the flaky test failures for all of these tests. And yet, it's only for one of these tests was the time value really a factor that would have influenced whether or not this test would have flaky test failures. In conclusion, we find that detecting flakiness is still a very challenging problem. What developers claim as fixes for these flaky tests are often unreliable, and that async wait is one of the most common category of flaky tests in both open source and proprietary software. To help developers with these flaky tests, I present here a study to characterize flaky tests and an approach to help balance the runtime of flaky tests along with the frequency of their flaky test failures.